Welcome to this video presentation on extended surfaces, commonly known as fins. Today, we'll be working through example 1, which involves calculating the thermal conductivity of a long rod acting as a fin. Let's delve into the problem statement. We have a long rod, 35 millimeters in diameter, with one end inserted into a furnace and the other end projecting into the outside air. After reaching a steady state, the temperature of the rod is measured at 2 points, 180 millimeters apart, and found to be 180 degrees Celsius and 145 degrees Celsius respectively. The atmospheric temperature is 25 degrees Celsius. Given that the heat transfer coefficient is 65 watts per square meter degree Celsius, our objective is to calculate the thermal conductivity of the rod. Now let's begin with the solution by outlining the given parameters. The diameter of the rod D is 35 millimeters. The atmospheric air temperature TA is 25 degrees Celsius. The heat transfer coefficient H is 65 watts per square meter degrees Celsius. For analysis, we'll consider the starting point x equals 0 at the first temperature measurement point and x equals L at the outer point, where L is the distance between the two measurement points, 180 millimeters. We'll assume that the end of the fin is insulated, which is a common idealization for long fins. Now, for an insulated fin tip, the temperature distribution is given by the formula theta over theta naught equals T minus TA over T naught minus TA, which equals the hyperbolic cosine of m times L minus x divided by hyperbolic cosine of m times L. Here, theta represents the temperature excess, P minus TA, and theta naught is the temperature excess at the base of the fin, T naught minus TA. Now at x equals L, this equation simplifies to theta L over theta naught equals 1 over hyperbolic cosine of m times L. Now from the problem, we can calculate theta L equals to 145 minus 25, which is 120 degrees Celsius, and theta naught minus TA equals 180 minus 25, which is 155 degrees Celsius. So 120 over 155 equals 1 over hyperbolic cosine of m times L. Now from the previous step, we have 120 over 145 equals 1 over hyperbolic cosine of ml. This means hyperbolic cosine of ml is equals to 155 over 120, which is approximately 1.292. Taking the inverse of the hyperbolic cosine of 1.292, we find that ml is approximately 0.747. Now we know that m is also defined by the square root of h times p divided by k times ACS, where p is the perimeter, ACS is the cross-sectional area. For a circular rod, the perimeter p is pi times d, and the cross-sectional area ACS is pi times d squared over 4. So substituting this into the formula m, we get m equals the square root of 4h over k times d. So we have two expressions for m, 0.747 over L and the square root of 4h over k times d. Equating these two, we get the square root of 4h over k times d equals 0.747 over L. So to solve for k, we can square both sides of the equation, and this simplifies to 4h over k times d equals 0.558 over L squared. Now rearranging and performing this calculation, we find that the thermal conductivity of the rod K will be approximately 431.34 watts per meter degrees Celsius. Thanks for watching. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so you don't miss out on our latest uploads.